All right, wonderful. Thank you very much. Hi, everyone. My talk, as Carrie mentioned, will be on the intersection multiplicity of plane curves. I'd just like to begin with, okay, let me see if that's working. There we go. Okay, so I'd like to begin with a quote by Ian Stewart. There is a word in mathematics for previous results that are later changed. They are called mistakes. So to motivate the concept, I'd like to begin with a result that is often called the crown jewel of intersection multiplicity, Bezo's theorem. It states that if f and g are polynomials with degree f equal m, degree g equal n, then the curves defined by the equations fxy equals 0 and gxy equals 0 intersect exactly mn times. Now, I would say that this is quite a beautiful result with the numerics working out in an almost miraculous way. But there is one small problem. The theorem is completely false. If you look at these examples in the plane, we have the parabola, the hyperbola, circle, and the x-axis. And as you can see, the result is false. The parabola does not meet the line at any point, neither does the hyperbola, and the circle meets it at only 1 point, even though Bezo's theorem would say that they should meet in 2 points, because these three are conics of degree 2, the line is degree 1 curve. So Bezo's theorem is false, or is it? Part, if you will, of this talk will be to show a way to undo the mistake and to make this theorem true by a little bit of fudging, if you will. So to see how we get to that, I'm going to quickly diagnose the 3 problems which are presented by these counterexamples. So the first problem is that curves might meet at imaginary points. We know that the parabola and the line, even though they do not meet in the real plane, do meet in the complex plane at plus minus I0. So the solution to imaginary points is, of course, to move to the algebraic closure. The second problem is that points, the intersection points might escape to infinity. We know that the hyperbola, even though it does not meet the line, does asymptotically get to the line at plus minus infinity. And the way to account for points at infinity is, of course, to move to the projective plane. The third problem, and the one which this talk will specifically address, is intersection points bunching up. Now, if you were to sort of imagine moving the circle up just a little bit, move it up a little bit, you will see that the line will then cut the circle at 2 points. But then if you were to move the circle back down until precisely the point where it is tangent to the circle, those 2 intersection points will come closer and closer together until they coalesce into 1. So intersection multiplicity ultimately is a way to count properly, to find a way to count the number of times the intersection points bunch up. Now, how do we do that? Classically, the way to approach this problem is by taking a concrete function, which you define to be the intersection multiplicity, and basically studying its properties. And there are 3 distinct ways to define this function. The first is the resultant method, which draws upon the elimination theory developed by Fermat, Newton, and Leibniz in the 1600s, which was a method for finding intersection points of curves by eliminating one variable. This was refined for multiple variables over the centuries and reached its zenith in the work of Hilbert, who used it most famously to solve all problems in invariant theory. And the modern way to formulate it is via linear algebra and determinants, creating something called a resultant. I have an example of it in this slide. To calculate the intersection multiplicity of these 2 curves f and g at 0, 0, you evaluate this horrible, horrible looking thing. I always like to include this example in all of my expositions on this because it's a good scare tactic, I feel, where sure, you can put this into a computer algebra system and get it to evaluate it for you, but it's pretty terrible to look at. And part of this talk will be showing a way to do this in a much simpler way. without having to mess with this horrible determinant. The second method of calculating intersection multiplicities is the branch method. It draws upon methods of complex analysis. Basically, you parameterize a curve at a point into its branches. The best way to intuitively understand what that means, consider the cuspidal cubic at the origin. You have one part, the upper part, and the lower part being its branches at the origin. Now, the methods for parameterization were developed by Puiseux in 1850 and later used by Cayley, Helfand, and Max Noether to define intersection multiplicity. Now, this method is very geometric because you can actually see what exactly a branch is. The problem is that it's not always possible to parameterize it in a way that allows its calculation to work. The third method is the local ring method, which was first used by Chevalley to study intersections. The basic idea is to form a local ring of functions, which I have as a heuristic an algebraic tangent space, although now that I'm speaking to algebraists, you all probably know more about local rings than I do. So there's no real need for the heuristic. The idea is to take a quotient of this local ring, calculate its dimension as a vector space, and then this gives the intersection multiplicity. The problem with this method is that it's hopelessly abstract and there's no geometric interpretation of this method, but it has the advantage of being much more closely related to the ideas of modern algebraic geometry, you know, schemes and sheaves and all that, for those for whom that means anything. Now, by taking those concrete functions and studying them, we can derive a number of properties which the intersection multiplicity satisfies. In 1969, however, William Fulton, pictured here, although not as he looked in 1969, decided to go the other way. Rather than beginning with the function and deriving its properties, he began with the properties and studied what this does to the function, or what this tells us about the function. Now, you might wonder what exactly is the point of this, because this seems like a lot of effort for no real gain. But there are a couple of advantages which are afforded by this method, the so-called axiomatic method. The first is that we get uniqueness out of the deal. Now, this is important for two reasons. First and foremost, if there were two or more functions that could give you a geometrically sensible intersection multiplicity, then of course the whole concept is completely ill-defined. You can't really talk about a intersection multiplicity if there are two possible values. The second, which is a sort of corollary or uniqueness, is that all three of the methods which I mentioned before, the branches, the local ring, and the resultant, all are actually equivalent. Even though all three of them are extremely different, and you would not guess at first sight that they all somehow do converge to the same answer. And the third, which is probably the most useful for practical purposes, is that the axiomatic method gives you much easier calculations. You don't have to futz around with determinants or parameterizations or local rings. So then the question is, what properties exactly of the intersection multiplicity do we need to focus on? So just to start with, I'm going to define my notation. K is an algebraically closed field. A2K is the Cartesian product of K with itself. F and G polynomials in two variables. Now, I'm going to work in affine rather than the projective space, despite what I said at the start, for the simple reason that transferring to projective is actually really easy. And the affine picture is a lot more clean, sort of from a theoretical perspective, when talking about intersection multiplicity. And so with that, the plane algebraic curve of F is a set of all points in A2K, which satisfy the equation fxy equals 0. And for notational purposes, F will stand for both the polynomial and for this curve that it generates. And with that, we will denote the intersection multiplicity with IPFG for the curves F and G at the point P. I just want to make a remark about products. If F is a factorization of polynomials, it doesn't have to be irreducible, just a factorization, then we know that Fp is equal to 0 if and only if at least one of the FIPs is equal to 0. Therefore, a point P is on F if and only if it is on one of its factors. But the key point basically is that a product of polynomials corresponds to a union of curves and vice versa. To make this easier on ourselves, we will use the terminology that the component is the curve generated by a non-constant factor of F, and a common component is the curve generated by a common non-constant factor of F and G. So with that, I can present the Fulton's list to begin with. Now, I'm just going to put it up here as a sort of homage to the master. I'm not actually going to use these axioms because this list is has a couple of redundancies and is more complicated than we need to. I just put it up here to mention that this is the original list, which was given by Fulton in 1969 for the properties that he will use as axioms of intersection multiplicity. Instead, I'll use a simpler set of axioms, which is in the book Algebraic Curves Over a Finite Field by Hirschfeld, Korczmarek, and Torres. The first property is that IPFG is equal to infinity if and only if F and G have a common component passing through P. I'll just give a quick example to show why this should be true. We have F, the union of the cubic and a parabola, and G is the union of the cubic and a line. F is in red, G is in blue, and the common component, the cubic, is in purple because red and blue. So for a point on this common component, such as -1, -1, we see here that at this common component, the two curves don't merely intersect, but are coincident. They stack on top of each other and intersect infinitely often. And for that reason, it makes sense to say that for a point on this component, the intersection multiplicity should be infinite. The second property is sort of the follow-up to the first, is that IPFG should be a positive integer otherwise, because we are counting multiplicity, so it should be an integer. Also, IPFG is equal to 0 if and only if F and G do not intersect at P, because you can't talk about multiplicities if they don't intersect at all. The third property is symmetry, which is obvious. No real need to explain why that should hold. The fourth is that IPFG is equal to 1 if F and G are distinct lines through P. Basically, we take the simplest possible curves lines and use them as our base for calculation. So if F and G are distinct lines through P, then they have multiplicity 1. The fifth property is a product property, that IPF with GH is equal to IPFG plus IPFH. To see why this should be true, we again just remember that the product of polynomials corresponds to a union of curves. So if we have here F, the line, and G, product of G1 and G2, the parabola and the custal cubic, we see that if we want to calculate the intersection multiplicity of F with G1, G2, it should be the sum of the intersection multiplicities of F and G1, so the line and the parabola, and then F and G2, which is the line and the custal cubic. The sixth property, the most mysterious one, is IPFG is equal to IPFG plus AF for any A in KXY. Now, this one is the most difficult to understand from a geometric point of view. And I'm just going to say that now that I have an algebraic audience for once, the simple reason for why this is true is because the ideal generated by F and G is the same as the ideal generated by F and G plus AF. And now I can state the existence and uniqueness theorem. There is a unique function, the intersection multiplicity, which satisfies these 6 properties, and it is given by this. This is the local ring definition, the dimension of the local ring, which is quotiented by the ideal of F and G. Now, you could have easily put the resultant or the branch calculation here. I'm just using the local ring because it's the easiest to write down, even though it looks pretty terrible. Right. So I mentioned before at the start that one of the advantages of this axiomatic method is that it makes calculations easier. And I'm just going to give the example of those two curves I mentioned with the resultant, with that horrible determinant, to illustrate why, or rather to illustrate that it is much easier to calculate with the axioms rather than with a concrete function. So we have here butterflies and or clovers, which pass through the origin. And we're going to calculate the intersection multiplicity of these two curves. So I've got the list of axioms up here in case anyone wants to follow this calculation with me. I'm just going to mention, I will use the symmetry property I3 without mention, because if I mention symmetry every time, this will take twice as long. So beginning with our two curves, the first step is to chop off the cubed bit. So I subtract the second from the first to get rid of the x squared plus y squared all cubed, leaving me with just negative 3x squared y squared on the left using I6. The next step is to chop off now the x squared y squared bit by multiplying this by a third and subtracting it from this side to cut that off, again using I6. Now, using the product property, I take the power down to sort of split the three factors apart. Next, again, the product property, this time on the left-hand side. Now I split the negative 3, the x squared, and the y squared. Again, the powers come down, so the 2 comes from the x squared, the 2 from the y squared, and now I'm left here with the negative 3 and x squared plus y squared. Okay, from there, negative 3 equals 0, as we all know, cannot ever be satisfied. So here, this is an empty curve and has no points. So we can cancel it out using I2, leaving us with this. Next, we again use the I6 property to chop off here we chop off the x squared bit, and here we chop off the y squared bit, leaving us with 2ip xy squared plus 2ip yx squared. Finally, we again take the power down using the product property, leaving us with 3 outside of 4ip xy plus 4ip yx. And now finally, we know that x equals 0 and y equals 0. The lines through the origin meet at 0, 0, of course. And by I4, if they're distinct lines through the same point, then the intersection multiplicity is 1. So we're left with just 4 and 4. 3 outside of 4 plus 4 is 24. And that gives you the intersection multiplicity at the point p equals 0, 0. So the takeaways from this calculation, first and foremost, as I hope you will agree, that was much easier than that pretty horrible determinant. We needed nothing more than elementary manipulations of polynomials. And the whole calculation was something that could have been done in theory by a competent high schooler. Now, I don't want to say that in general, this will always be, if you will, so easy. It does require, given a complex example, a sort of bit of ingenuity and sometimes a bit of luck. But if the calculation is not simple, I would say the list is almost simple, with apologies to all the group theorists. The second takeaway is that, of course, we don't need to tinker with determinants, parameterizations, or local rings. Again, it's just polynomial arithmetic, nothing fancy. It's all very elementary ways to calculate intersection multiplicity. And a third takeaway, which during my sort of study of this was a bit of a surprise, even though now I think about it, it's really obvious, that we find intersection points as a bonus. So notice that during that calculation before, I didn't actually use at any point the fact that p is equal to 0, 0. It just had to be at the end because we were left with two lines, x and y, and both of them pass through 0, 0. And because the axioms preserve intersection multiplicity, they must also preserve intersections. So we get, as a bonus in the calculation, all the intersection points of our two curves. And so with that, I will finish off by just showing how you fix Bezos' theorem. And this is its correct statement, the one that is true. So let f and g be projective curves over an algebraically closed field, degree f equal m, degree g equal n. If they have no common components, then they intersect exactly mn times, counted according to multiplicity. And that's where I'll leave it there. Thank you all very much for listening.